Precipitable water graphical technique. In this video we're going to step through an exercise where you calculate the precipitable water for a trace using a graphical technique known as the equal areas method. On the left hand side you can see a profile of dew point temperature, and in a minute I'm going to get you to pause the video and plot this on a skew-t log P. Once you've done that, what we're going to do is calculate a mean value of mixing ratio for each of the 4 layers indicated and calculate the precipitable water for each of those layers. Then we'll sum them up to get the total precipitable water for the trace, and then finally ask the question, where does the major contribution to precipitable water come from? Now of course we don't do this operationally, but the whole idea is to get us to understand what's happening in the calculation of precipitable water a little better. So pause the video now and plot this profile. How did you go? You should have a dew point profile now. Here's a sample dew point profile with 4 values of dew point temperature and 3 connecting lines. How do we calculate the mean mixing ratio for this layer? What we're going to do is choose a best value of R such that the area between that line, that isopleth of mixing ratio, and the dew point profile on the left hand side is equal to that on the right hand side. So what does that look like? Here we've chosen a value of R that enables the areas in green, that is A, to be approximately equal to the areas in blue, that is B, on the right hand side of the profile. And so what you do is you get a ruler or something like that with a straight edge and move back and forth until you were satisfied that you had equal areas on either side. In this case, the line that does that gives us the mean mixing ratio for the layer is approximately equal to 9.3 grams per kilogram. Now I want you to pause the video again and do this for the 4 layers of the trace that you drew earlier. So how did you go with that? Now what's shown is the trace, roughly plotted out, and 4 values of mean mixing ratio for the layer, and you can see what's been done is that the areas are shaded in to try and indicate that there's equal areas either side. This method takes a little bit of practice, but nonetheless what you can see once we've done that is that the mean mixing ratio for the layers decreases with height. And we've talked a little bit about this earlier. The source of moisture is the surface, and then vertical motions transport water vapor upwards. So the largest contribution to precipitable water happens in the lowest layer, where the mean mixing ratio is 15 grams per kilogram, and you see for the top layer it's about 0.3. When we add all those values up, or rather we calculate the precipitable water, here are the values. So there's 269 tenths of millimeters in the lowest trace, down to 5 in the top. When you add up all of those, it's about 43 millimeters roughly. The calculated value for this particular trace was 43.7, so it's not a bad approximation. And as we've noted, most of the moisture resides in the lower part of the troposphere, and that's what makes the largest contribution to the precipitable water. If we did this calculation for every single layer, here's what you get, and you get a value that's very close to the actual value itself, so that's somewhat tedious. What the whole exercise demonstrates is that the largest contribution to precipitable water is in the lowest parts of the troposphere, and we use it from day to day as a forecast parameter for things like heavy rainfall.